All right, should be recording. So we're looking at compound J here. And compound J is C3H6O. So that's pretty simple, right? There aren't that many different ways of connecting C3H6O. So what are we going to do first?
Degrees.
Degrees of unsaturation. So saturated would be C3H8. 8. There's no nitrogen or halogen, so I just take those 6 that are there. There are 2 missing.
1 degree.
1 degree of unsaturation. So we can eliminate some things. What can we eliminate?
Alkynes and benzene.
Alkynes and aromatics. All right, so we know there's no alkynes, we know there's no aromatics. Do you see any broad singlets in the spectrum?
No.
No broad singlet. What does that eliminate?
It being an alcohol.
So that oxygen is probably not an alcohol. So now, let's take a look. What can we actually see? Right, here's the TMS peak at 0. You'll notice there's a little blip at 2-ish. That's acetone from not cleaning the tube properly. And down here at 7.26, you'll see the little chloroform residual, since there's nothing in the aromatic region. Right, we've already eliminated aromatic, but if we hadn't, we could eliminate it by the fact that there's nothing between 7 and 8. What else can we eliminate based on looking at the spectrum?
Anything high, like carboxylic acid, stuff like that.
Yep, so we know that it's not a carboxylic acid, right? We eliminate that because, again, there's no broad singlet. And that would be between 11 and 13. We're not even seeing that spectrum, so we know it's not a carboxylic acid.
No ketones.
You can't necessarily say that yet, right? Because
I think we can say it's not an aldehyde, though.
we can definitely say it's not an aldehyde, right? There's no peaks between 9 and 10, so it's not an aldehyde.
I also don't think it's a single bond to the O, because the peaks are more between 2 and 3, not like 3 and 5.
Yeah, but I'm confusing you with this spectrum intentionally, so there's something else we can eliminate. Do you see any peaks between 5 and 6 ppm?
Oh, it's not an alkene?
It is not an alkene. So the degree of unsaturation is not a carbon-carbon double bond. Right? It can't be an aromatic. What's that?
I was just going to ask, is it a cyclic alkane? Is that where the degree of unsaturation comes from?
It's likely that the degree of unsaturation is a ring, yes. Because it's not coming from a carbon-carbon double bond. It could be coming from a carbon-oxygen double bond. We haven't gotten rid of that. We know it's not an aldehyde, but we haven't really addressed whether it could still be a ketone. But it's likely that it's from a ring of some sort. Right? Usually you can't say that it's a ring because of something you're seeing. You end up saying that it's a ring because of something you're not seeing. So what else? What are we going to look at first in the NMR?
I think the peak between 1 and 2, it tells us that there's likely a CH3 group.
So there's a delta at about 1.3 ppm. It's got a 3 hydrogen integration, which is likely a methyl group. So I've probably got a CH3. And it's a doublet. Why is it a doublet?
The single adjacent hydrogen?
One adjacent hydrogen. So this carbon here has one hydrogen on it and 2 things that aren't hydrogen. What about the rest of the spectrum? You got a bunch of peaks between 2.5 and 3.5, right? There's 3 separate peaks, each with a 1 hydrogen integration. What does that tell me?
Could that be
Three
those
magnetically distinct.
They're all magnetically distinct. Yep. Could that be what? What did you say?
I'm guessing it might be the propane ring. If 3 different
So-
signals.
So it can't be a cyclopropane, right? Because we got a CH3. Right? We
It's
can't.
gonna be a C and an oxygen ring.
So we've used, right? We've used C2H4. So what do we have left? If we subtract that,
CH2O.
so we got 1 carbon, 2 hydrogens, and an oxygen remaining. We know we have to have a CH3 group. We know the adjacent carbon has to have a hydrogen, and then it's got to have 2 other things attached to it. The only way to do that is to make it the 3-membered ring with the oxygen, or an epoxide. These 2 hydrogens now, although they're on the CH, right, they're on the same carbon, they're not magnetically equivalent, because this one is trans to that hydrogen and this one is cis to that hydrogen. So those 3 hydrogens on the epoxide, those are the 3 hydrogens between 2.5 and 3.5. And in this case, we've got hydrogens that are going to be splitting each other and not with the same coupling constant, because the cis, the trans, and what we call the geminal coupling constants are all different. Right? So this is a geminal, these 2 hydrogens that are attached to the same carbon. Gemini comes from the same root as twins. Those 2 hydrogens are twinned. And then the cis and the trans coupling constant. So what would we expect this hydrogen to look like? What's it split by?
Further down, maybe?
What's that?
Would it be further downstream?
We might expect this case, right? We're going to expect this one to be different from these 2. These 2 should be closer together than either of them is to this one, because this one has the methyl group. Is the methyl group pushing electrons in or pulling electrons out? Of the system? Is it an electron donor or an electron withdrawing group? Think about hyperconjugation.
It's donating electrons in.
It's donating electrons in. So we might expect this hydrogen to be shifted less far down than the other 2, right? Because the methyl group should be pushing some electrons in, which will mitigate the effect of the electron withdrawing oxygen a little bit. So it's likely that in this case, this one up here is the one that's unique, that's on the carbon by itself, and these 2 that are further down are the other 2. That's not definite, but it's possible. So what would we expect to see for that hydrogen if the coupling constants were all kind of distinct? It'd be a complicated pattern. Maybe I should ask the question, what would we expect to see for this one first? It should be split by its partner and also by that one. So we should see a J geminal and a J trans. And we should expect those to be different. So we expect to see a doublet of doublets. Or 4 peaks. And we expect those peaks to have a 1-to-1 to 1-to-1 ratio of intensity. What would we expect to see for this one?
Doublet of doublets.
Also a doublet of doublets, because we'll have a J geminal and we'll have a J cis. Usually that J cis is smaller than the J trans, right? So we might actually see some overlap. And then for this one, that's kind of a mess, right? Ignoring the methyl group, we should see a J cis and a J trans. So that should be a doublet of doublets. But then we also have the methyl group. And what will that split it into? If you ignored these peaks for a second and just looked at the adjacent, right? This hydrogen has that adjacent methyl. Because these 3 are magnetically equivalent, yeah? What are 3 magnetically equivalent hydrogens split? Quartet, right? So we might expect to see a doublet of quartets for this. That would be a mess. Right. Probably that's not going to be clearly split, because that would be 16 total peaks, right? We're probably not going to get those clearly separated from each other. This one does here, right? If you look at the region between, right, that's closest to 2, that one really is kind of nice, 4 peaks. That is a doublet of doublets. That's a nice pattern. This one looks like a triplet, but that may be because the coupling constants just happen to be about the same. And then this one's kind of messy, right? It's kind of a doublet of doublets, but then it's got some other stuff scooting underneath it. This is an ABX pattern. It's just not as clean as an ABX pattern as you usually see for an alkene, but it's definitely consistent with having 2 hydrogens on 1 carbon splitting each other, and then 1 carbon on an adjacent hydrogen. It's really the only way, this epoxide is the only way you can introduce that degree of unsaturation and not have symmetry. If it were a ketone, right, the only way you're going to make this into a ketone is by making it acetone. Right, that's the only possible C3H6O that has a carbonyl group in it, and it's obviously not acetone, because acetone would only have a single peak at 2.1, where all 6 methyl groups, all 6 hydrogens rather, would be identical. So it's that doublet at 1.3 parts per million. That's what tells us what the whole structure is, because as soon as we determine that we have to have a methyl group next to a CH, there's really no other way of putting the rest of the spectrum.